This is an Excel QM tutorial application for production scheduling using simple linear programming.
One of the linear programming application in operational research is the production scheduling. Setting a low-cost production schedule over a period of weeks or months is a difficult and important management in most plants. So the production manager has to consider many factors like labor capacity, the inventory and storage cost, the space limitations, product demand, and labor relations. Because most companies produce more than one product and the scheduling process is often quite complex. Basically, the problems resembles the product mix model for each period in the future. The objective is either to maximize profit or minimize costs of carrying out the task. Production scheduling is amenable to solution by linear programming because it is a problem that must be solved on a regular basis. When the objective function and constraints for a firm are established, the inputs can be easily be changed each month to provide an updated schedule. So now let me teach you how to use the Excel QM in solving linear programming for production scheduling. So now here is an example for production scheduling. Greenberg Motors Incorporated manufactures two different electrical motors for sale under contract to Drexel Corporation, a well-known producer of small kitchen appliances. Its model GM3A is found in many Drexel food processors, and its model GM3B is used in the assembly of blenders. 3 times each year, the procurement officer at Drexel contracts Erwin Greenberg, the founder of Greenberg Motors, to place a monthly order for each of the coming 4 months. Drexel's demand for motors varies each month based on its own sales forecast, production capacity, and financial position. So Greenberg has just received the January to April order and must begin with his own 4-month production plan. So this table shows the January to April order for GM3A and GM3B. So of course, with that production planning, they must also consider the several factors. So number one factor is the company must meet the demand for each of the 2 products in each of the 4 months. And then the company would like to have 450 units of the GM3A and 300 units in the GM3B in inventory at the end of April, as demand in May is expected to be somewhat higher than demand in the previous month. The number 2 is there is a carrying cost for any inventory left at the end of the month. So producing too much either product may not be so desirable. So the carrying cost will be GM3 is $0.36 per unit per month, while the carrying cost for the GM3B is $0.26 per unit per month. Number 3 is the company has been able to maintain a no layoff policy and it would like to continue with this. This is easier if the labor hours do not fluctuate too much. So the schedule would require 2,240 to 2,560 labor hours per month, and the GM3A requires 1.3 labor hours per unit, while the GM3B requires only 0.9 labor hours. Number 4 is the warehouse limitations cannot be exceeded without great additional cost. So there is room at the end of the month for only 3,300 units of GM3A and GM3B. The production cost is currently $20 per unit for the GM3A and $15 per unit for the GM3B. However, each of these will increase by 10% on March 1 as a new labor agreement goes into effect. So as we formulate the linear program, we will consider the factors related to the cost and the labor hours per month and how demand is met with both production and inventory on hand. So to help us with understanding, let's try to determine the number of labor hours, the number of units left in inventory at the end of each month, and then the total cost is exactly 1,000 of the GM3A and exactly 1,200 of the GM3B were produced each month. So first is we begin to identify the objective. As we all know, we will minimize the total cost, including the production and the carrying cost. So for the objective minimization, let A1 to 4 be the demand for the GM3A. B1 to B4 will be the demand for the GM3B. And then inventory A1 to 4 for the inventory of GMA3A. And then inventory of B1 to 4 is for the inventory of GM3B. As you can see in the minimization cost, they already have a value on each of the variables. So from this one, as we can see, it is already stated from the production cost that there is $20 for GM3A and $15 for GM3B. So there is an increase by 10%. So 20 plus 20 for the January, 20 for February, and then we will just add the 10% increase from the 20, which is 22 from March, and then 22 also for April. And then also for the demand of GM3B, we will have $15, 15 also for February, and then we will also add the 15 times 10%, which is 16.5 for the month of March, and then 16.5 also for April. And then the inventory, so as we also see on the factors, it states there that the carrying cost is 0.36 for GM3A and 0.26 for GM3B. So we'll just add it on side of the variable, which is 0.36 for the A1 and then 0.26 for the inventory of B1 to 4. So for the constraints, we all know that we have several factors to identify. So first is the demand constraint, second is the labor hours, and the third is the storage capacity. So for the first model, GM3A, we have for demand constraint. So which means that there is one constraint for the 4 months. And then also for the GM3B. Second is, we have 2 constraints for the inventory at the end of April. So as we can see, it is stated there that there is an inventory combined. An inventory at the end of April. So there is 2 constraints for that, because one for the GM3A model and one for the GM3B. And then for computing for the labor hours demand, we will have the minimum and the maximum labor hours, which is also 4 constraints for each month. And then lastly is 4 constraints for inventory storage capacity each month. Then in setting up the constraints, we will also recognize the relationship between the last month ending inventory and the current month production through the sales to the Drexel this month. So as you can see from this formula, inventory at the end of this month should be equal to the inventory at the end of last month plus the current month's production minus sales to Drexel. But while the constraints could be written in this form, inputting the problem into the computer requires all variables to be on the left-hand side of the constraint. So we will gonna just rearrange it. So there will be a value for the right-hand side. So the inventory at the end of last month plus the current month's production minus the inventory at the end of this month will be the sales to Drexel. So here it is. As you can see, for the demand in January, we have A1, and then we will just gonna subtract it from the inventory of A1 or the January. And then for the second is inventory of January plus the demand of February minus the inventory of February, and so on and so forth. And also we will also find the inventory of GM3A at the end of April and the inventory of GM3B at the end of April. So for the maximum and minimum number of labor hours, 1.3 and 0.9. So as you can see on the stated factors, there is a maintaining production schedule that require 2,240 to 2,560 labor hours per month, which is 1.3 labor hours per unit required for GM3A and 0.9 labor hours for GM3B. So we're just gonna input the value here, and then since it is minimum, we will be using the greater than, which is 2,240, and maximum is less than or equal to 2,560. So there is a 1 to 4 because we have the 4 months and also 4 months for the GM3B model. And the storage capacity constraint, which is inventory for January for model A
and then inventory for GM3B, which is less than or equal to 3,300. And for the non-negativity constraint, all variables is greater than or equal to 0. So as we all identified and very clear, let's now proceed to Excel. So again, let's just click the Excel QM, plug in all the values. Let's click the data, then click the solver. Data and solver. Then click solve. Okay, so it states there that the solver found a solution and all constraints and optimality conditions are satisfied. So let's click OK. So as you can see, the result shows the variable column and the objective. So which means that the total cost for the 4 months is 1,609,295. And for the variables, it means that the demand for January will be 1,276.9. Then demand for February will be 223.08. For March is 1,757.7, 792.31 for April. And then for the GM3B model, it has 1,000 for January, 2,522.2 for February, 77.778 for March, and then 1,700 for April. For their inventory, GM3A model will have a 476.92. There will be no inventory for February. There is 757.69 in March. There is 450 in April. As for the GM3B inventory, there is 0 inventory for January. There is 1,322.2 for February. No inventory for March. And then there is 300 inventory for April. So from these results, let's try to make a production schedule. So for the variables of A1, there is 1,776. So we will round it up. It will be 1,277 for January, 223 for February, 1,758 for March, and 1,000 for April. And then for B1 here, so it means that it is for GM3B. So, okay, this is not 1,000. This is 793. And then 1,000, then 2,523, then 78, and 477. Then for the inventory, so here, inventory will be 477, then 0 for the February, then 758 for March, and 0 for April. 450. And then next is 0 for January, 100,322 for February, 0 for March, and 300 for April. So as you can see, we really consider the factors earlier that the inventory at the end of April must be 450 for GM3A and 300 for GM3B. So the labor hours will be January is 2,560, then steel 2,560, and here is 2,355 as you can see here, and then here is 2,560, 2,555 and 2,560. So now we have our production schedule using the simple linear programming for production scheduling, having 3 types of constraint. That's all, and I hope you can explore more about the application of linear programming.